Okay, welcome to our lab for Tuesday morning and every morning and whatever, I don't even know anymore. Okay, so like I mentioned before, I started recording this. You need to have this document, the glomerular filtration, up here at the top that I uploaded yesterday, and so we're just gonna go through this video or go through this packet. And so you need to know everything in this packet. Let's see. Oh, I didn't record that. Okay, so I'm going to decide how far we go in this, just as I'm looking through this packet. Okay, so we're going to watch a little video thing from the interactive physiology, watch some things, and then I will stop it and we'll talk about things. We'll fill in the answers, that kind of thing. Okay, I'm just going to jump in and then we'll just go. So let me share my, hang on, let me get this going first.
Okay. Involves three main processes.
Okay, all right, so share my screen. All right, let me know if you can't hear this very well. I can try to adjust some sound. And get rid of us. So feel free to chat me if you can't hear very well. Okay.
Filtration, reabsorption, and secretion. During filtration, large quantities of water and solutes pass through the filtration membrane from the blood into the glomerular capsule.
Okay. All right. Oops. Let me take that back just a hair. All right. So, so here we are in the glomerulus and the Bowman's capsule. So let me just annotate a few things. Trying to find my little things. There we go. Okay, so do this in green. Green will show up. All right, so just to orient you so that you know what you're seeing here, because there's always different ways of drawing in where things are. So this is the afferent arteriole coming in this way. Okay, so this is our afferent arteriole. And so blood will be delivered, all of this in here, so all of this stuff in here. Okay, this is all glomerulus. Okay, and then this is the efferent arteriole, so blood will be leaving the glomerulus through the efferent arteriole. And then out here, let me make my line a little thicker. Okay, so then out here, I feel like I'm tagging because I have a little spray can. So all of this out here is the glomerular capsule. I think it says right there, glomerular capsule. Now here's the thing. Remember when we were taking a look at the structure of the nephron last week, that we have the capsule, so we have the cup part on the outside, but then notice that the cup curves around and then it's going to wrap itself all the way around all of the glomeruli, all of the capillaries. Okay, so it wraps itself around and then it covers over the capillaries. So this yellow right here, all of this yellow stuff is actually material, they're cells, podocytes, that are going to wrap themselves around the capillary, because the capillary is actually this, oops, hang on, is actually on the inside. So here is the capillary wall right there. Okay, so then between the capillary wall and the podocyte right here, then we're going to have a filtration membrane that's going to be just like the respiratory membrane that we had within the lungs. Okay, so material will be leaving the blood vessel, and then it's going to go through the blood vessel wall, through the podocyte, little filtration slits, these little little zigzaggy stuff right here, and it'll come out, and then it'll go into the capsule, and then it'll all collect down here, and then it'll dump and go into the rest of the nephron. Okay, Does anybody have any questions on that? I know that was kind of like, oh, but okay. All right, so let's move on. Let me get rid of my, oops. Oh, okay. All right. Oh, and then get rid of that. Okay.
Your goals for learning. To preview the three major processes, we'll use the simplified diagram of a kidney nephron showing the afferent and efferent arterioles, glomerular capsule, capsular space, glomerulus, the beginning of the renal tubule, and the peritubular capillaries. Click the glomerulus to see the renal processes. The formation of urine begins with the process of filtration. Fluid and small solutes are forced under pressure to flow from the glomerulus into the capsular space of the glomerular capsule. Now click the tubule to see the second process. As this filtrate passes through the tubules, specific substances are reabsorbed back into the blood of the peritubular capillaries. Now click the peritubular capillaries to see the third process. In addition, some solutes are removed from the blood of the peritubular capillaries and secreted by the tubular cells into the filtrate to fine-tune the composition of the blood.
Okay. So we talked about these three processes last week when we were looking at the anatomy. So let's just review again what's right here and then where stuff is moving, because this shows it really well. So, so here we have the afferent arteriole, we have the glomerulus. So this is where filtration happens. Okay, so filtration happens between the glomerulus and the glomerular capsule. So all this yellow material is all the filtrate coming out, essentially plasma coming out and collecting in the glomerular capsule. So filtration, you can see, is going to go from the glomerulus into the glomerular capsule. Then that material, if we look, it's going to come down this way. Oh, those other arrows are lost. So reabsorption is going to be through these simple cuboidal cells of the tubule, of the proximal convoluted tubule, and they're going to go, so that material is going to go out this way and into the peritubular capillaries, because that's what these things are right here. So filtration is glomerulus or capillaries to tubule, and then reabsorption is tubule to capillaries, and then here in secretion, like it says, some solutes are removed from the blood of the peritubular capillaries, secreted by tubular cells into the filtrate. So we're going to take them from here, and so we removed them from the blood, and then these cells here are going to secrete them, as this arrow is showing, back into the tubules so that we can finally excrete them. Okay, so remember, filtration, reabsorption, secretion, and then which direction the material is going. So filtration is blood to tubule, reabsorption is tubule to blood, secretion is blood to tubule. Okay. All right.
The rest of this topic covers filtration, while the filtrate processing topics in this module will cover reabsorption and secretion. Click the glomerulus, tubule, or peritubular capillaries to revisit any of these processes. A coffee maker provides an everyday example of filtration. The paper filter acts as the filtration membrane. It holds back the large coffee grounds while letting water and small solutes like caffeine and flavor molecules pass through. A force is required to drive this process. In a coffee maker, it's the force of gravity. What force would you guess drives filtration in the glomerulus? Select the correct answer by clicking the appropriate box. Yes, blood pressure is an important variable in the effective filtration of the blood. Just as a filter keeps grounds out of your coffee, the glomerular filtration membrane keeps blood cells and proteins out of the urine passageways. This filtration membrane is composed of three layers: fenestrated glomerular endothelium, basement membrane, and the many filtration slips formed by pedicels of the podocyte.
Okay, so we haven't done anything in the packet yet. We're almost there. Let's make a note of this structure of the filtration membrane. So I will give things different colors. Okay, so let's do the filtration, the fenestrated capillaries. Okay, so here, capillary, then there's a space, okay, and then we should have some more little spaces right here, and fenestration. So now where my arrows are going, that's not a very good arrow, are my fenestrations. Okay, so fenestrated capillaries, remember, are those that have pores in the wall. Then we have a basement membrane that is right here. Oops, I made it a little thick on that side. And then we have the podocytes, or the filtration slits. And so the podocytes are going to wrap themselves, let's see, they're making the podocyte the black thing. Okay, so here's part of a podocyte, here's part of a podocyte, part of it right here. So all this black stuff. And so the filtration slits are these openings right here. So whenever we're filtering things, yeah, there's one right there. There's one right there. Okay. So when we're filtering, here is the pathway that the material needs to take. I'll make it red. So it's going to have to come through a filter or a fenestration like this. Then it's going to go through the basement membrane, and then it's going to go through a filtration slit. So fenestration, basement membrane, filtration slit. Okay, in every one of these cases. Let's find another. Here's a better one. Okay, and then out through a filtration slit. Okay, so fenestration, basement membrane, filtration slits is the order of the passage of the material as it leaves the glomerulus and goes into the capsule. Because all of this in here, this is all capsular space. All of that I scribbled on. All right. Okay, now we're actually going to go into questions on the packet.
Passage through the filtration membrane is limited not only on the basis of size, but also by charge. Now click the filtration membrane to see an animation of glomerular filtration. Glomerular filtration is a process of bulk flow driven by the hydrostatic pressure of the blood.
Okay, so in question number 1, what force drives filtration at the glomerulus? You can put either thing. You can put just blood pressure, because she said that a little bit earlier, or you can put hydrostatic pressure. But question number 2 is this sentence right here. Glomerular filtration is a process of bulk flow driven by hydrostatic pressure of the blood. Okay, so in the case of bulk flow, we just have material leaving. It doesn't matter what size it is. It doesn't matter what anything about it. We're just pushing stuff out because it's going to get pushed. It's going to get pushed out through the fenestrations, go through the basement membrane, go through the filtration slits, and then on into the rest of into the nephron. And hydrostatic pressure is what's going to do it. Just like we saw with the coffee grounds, how does filtration happen? Hydrostatic pressure drives filtration. Okay.
As you can see, small molecules pass rapidly through the filtration membrane, while large proteins and blood cells.
Okay, as we're watching material pass through, we can see these green things fit through, the red things, the blue things fit through, these little purple things. But these purple things, these magenta colored oval thingies don't. And then of course the red blood cells not going to either because it's far too large. But these pinkish purple thing, magenta colored things, those are albumin. And so this is the albumin that's going to stay within the capillary and cause the osmotic pressure to bring fluid back from the glomerular capsule back into the glomerulus, so that just like in a regular capillary bed, so that we don't lose all of our water and then everything become thick and sludgy within the capillary and not have an opportunity to flow. So remember, these guys are albumin.
Are kept out of the capsular space. You can probably guess the severe effect on blood and urine composition if the filtration membrane is damaged or destroyed.
Okay, so when the filtration membrane is damaged or destroyed, anything can get through. And so there are two things, and remember this for always. We'll talk about it again later, but remember for always, there are two things you should never ever find in urine. One is blood and other blood cells, so red blood cells, white blood cells, platelets. I should never find that in my urine, and I should never find protein in my urine. Albumin or any other kind of protein, I should not find that in my urine. If I do, then we know we've either got a problem with our filtration membrane, we have glomerulonephritis, caused, from a kidney infection or something like that, or we have kidney stones, which we'll talk about when we actually get into this chapter after we take next week's test on respiration and digestion. Okay. So remember, no blood cells, no protein in your urine ever.
The fluid and solutes collecting in the capsular space is called glomerular filtrate. Now click the pipette to take a sample of the glomerular filtrate and see what it contains. Now click the Analyze Filtrate button to determine the contents of this sample. Our sample from a healthy person shows the common components of filtrate to be water, ions such as sodium, potassium, and chloride, nitrogenous wastes such as urea, uric acid, and creatinine, and useful organic molecules, including glucose and amino acids.
Okay, so I want you to fill that out now for question number 3. So the common components of the filtrate are divided into 4 categories. These include, so water, ions, make sure you list the ions, sodium, potassium, and chloride, nitrogenous wastes, urea, uric acid, creatinine. And this is really, so the two things that we're trying to get rid of as you're filling this out, the two things we're trying to get rid of in our kidneys are the nitrogenous wastes due to protein metabolism and water, because we drink more water than we need. And so we're making sure that the excess water that we take in goes back out. Let's take, for example, because you're probably thinking, I drink more water than I need. What's that all about? We drink a lot more water than we need. And what are we looking for in our urine? We're always looking for it to be really clear, that we don't want it to be dark yellow color. And so there are some organisms that never drink anything, and the only water that they produce in their bodies is metabolic water from cellular respiration, and any kind of water that may be in their food. So a really good example of this is a kangaroo rat. And so kangaroo rats never ever drink. Yay, Josh Dixon! You almost stole my thunder because I didn't click on that till after I said it. So they never ever drink. What they do is they put their seeds in their burrows, and that will absorb water. And so it'll like double the weight of the food that they're eating. So then they eat their seeds, and then they don't ever urinate either. Birds don't urinate. I don't know if you knew that, but when a bird poops on you, the white stuff that a bird poops on you is its nitrogenous waste. And so it's pasty. And so kangaroo rats, same thing. Oh man, you guys. Okay, when I just realized this. Hang on, I'm gonna go find it. I'll be right back. Don't go anywhere. Write some words down. Oh. Okay, I'm back. Thanks, Jamie, for talking to people while I was gone. Okay, so, oh my gosh, friends, this was even in my office. I ran around the lab trying to find, I could only find the gross stuff. Okay, see this white powdery stuff? It's not cocaine. I don't think you can snort it. I'm trying to get to where you, oh, there we go. Okay, so right in front of my face, we can see it really good. Okay, this is tortoise urine right there in the bag. So my tortoise Stanley, she when she poops, then she also has white stuff like a bird comes out, and it's all dry like this. This is like really freshly collected nice stuff. Okay, and then I have another bag of it. So there's another bag of it. Do I collect my tortoise urine? I absolutely do. Here's a big old chunky bag of it. This was stuff, let me get it in front of my face. Okay, there we go. This was stuff that had been out there for a while, and it got gross and yucky when I collected it. So yeah, my tortoise, she never urinates either. But she will urinate as a protective mechanism, which will then dehydrate her and kill her. So you don't ever want to scare a desert tortoise, or they'll void on you, and then that can cause them to die. So anyway, I love that about my tortoise. Not that she's going to die, but that she doesn't ever pee. Okay. So you wrote down all of those things. So anyway, so the kangaroo rat, yeah. And like Geronix, I'll have to show you a picture of a Geronix that we have at the zoo. No, you are not gonna fail. And you guys can Zoom together if you want. So I haven't even done anything yet today. Nicole, you're fine. You're gonna be all right. Okay. But yeah, you can Zoom with each other, or who knows what you can do, and everything is gonna be good. Everything's gonna be good, friends. Trust me, it's gonna be good. Okay. All right. So, okay, so here we go.
The concentration of each of these substances in the glomerular filtrate is similar to its concentration in plasma.
Okay, so that's another concept, is that, hang on, let me get my text. Okay, and I'm gonna type it right here so you can add this in. Filtrate is isotonic to plasma. Okay, so, oh, Marcus, yep. Okay, so when the material gets filtered, what the concentration of that material that's in the plasma is going to be the same as what comes out in the filtrate. Okay, so I have the same concentration of glucose in my bloodstream as I have in my filtrate. So if I had higher concentration of glucose in my in my bloodstream because I was diabetic, I'm going to have a lot more here in my filtrate, and then it's going to come out in my urine, and then we'll talk about why it comes out in your urine when you're diabetic. Okay, so always remember this filtrate, so the material that's coming out of here at the glomerulus is the same concentration as what your plasma is. Okay. All right, so let's move on. Oh, I gotta get rid of that. Okay.
How might the contents of the filtrate be altered if the filtration membrane is damaged or destroyed? More than one answer may be correct. Yes, producing a condition called proteinuria. Yes, depending on the amount of damage, this condition is called hematuria.
Okay, so remember I told you if the filtration membrane is damaged, then you'll have protein in your urine and blood cells in your urine, neither one of which you ever want. And so when my dad started to get sick, and they did some some blood tests on him, some urine tests on him, and they discovered that he had protein in his urine. And then he had to go to the nephrologist, and we ended up, he only had like 13% kidney function left. And then he had to go on dialysis. So what caused that problem? Why was he having protein in his urine? Well, because my dad had a high blood pressure that he wasn't treating. So what's going to happen if you're going to keep pushing against the capillary wall right here, push, 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 is that capillary wall going to, and that filtration membrane, is it going to be able to withstand the pressure? No, it's not. And so now we've got lots of stuff. It's like my dad's blood pressure tore leaks into his nephron here through the glomerulus, and then stuff was just dumping in there. Okay, and so it wasn't being filtered properly.
Just as gravity draws water through a coffee filter, so glomerular hydrostatic pressure promotes filtering of the blood. The blood pressure in the glomerulus averages 60 millimeters of mercury.
Okay, so question number 4, blood pressure in the glomerulus is about 60 millimeters of mercury. Remember that we said the blood pressure in a regular capillary is about 35 millimeters of mercury. And hang on, I'm trying to help Christiana get in. And so there's a lot more pressure in a glomerulus. So as the afferent arteriole is bringing blood into the glomerulus, the hydrostatic pressure is a lot higher than what we see out in the regular capillary beds of the body. So that's why we get so much filtration in the kidney, is because the hydrostatic pressure is so high. Now, what's going to cause the hydrostatic pressure to be high? So I want you to remember this. Maybe you could put a little note next to 4. Okay, here's our afferent arteriole again. Okay, so here's the afferent arteriole. Oh, that's a bad color. Okay, yellow. Okay, so that doesn't work. Okay, so our afferent arteriole is short in length. Okay, so it's short. So it's bringing a lot of blood right directly from the vasculature right to the nephron, and then it's has a large diameter. So there can be a lot of blood flowing into it. And so if I have a lot of blood flowing into the capillary, or from the arteriole into the capillary, it's going to push out with a lot of force. Okay, so we're going to be pushing out with a whole lot of force. All right, so lots of blood flow within the capillary because of the short, large diameter afferent arteriole creates this large hydrostatic pressure right here. Okay. All right.
This unusually high capillary pressure is the result of the short, large diameter afferent arterioles conveying blood at high arterial pressure directly to the glomerular capillaries. The small diameter of the efferent arterioles leaving the glomerulus also helps maintain the pressure by restricting the outflow of blood.
Okay, that's also a really important concept, is that the efferent arteriole is very small in diameter. So lots of blood comes in, but blood doesn't leave as much. So I get a lot of backup inside of the glomerulus, and that's going to also contribute to this large amount of force that's pushing the filtrate out, or the plasma, out of the capillaries of the glomerulus and into the glomerular space. Okay.
However, the glomerular hydrostatic pressure is opposed by 2 forces that reduce the flow of fluid into the capsular space. Fluid already in the capsular space creates a back pressure that resists the incoming fluid. This capsular hydrostatic pressure averages 15 millimeters of mercury. The second opposing force is the osmotic pressure of the blood in the glomerular capillaries. Remember that the capillaries retain proteins, which become more concentrated in the blood as the filtrate flows out. Because of these proteins, the osmolarity of the blood is higher than the osmolarity of the filtrate. The osmotic pressure of the blood, or its tendency to draw the fluid back in, averages 28 millimeters of mercury. The
Okay.
algebraic sum of these three forces
Oh,
produces the net filtration pressure of 17 millimeters of mercury.
okay. So in question number 5, we have two forces that are opposing this outward flow of filtrate. So one is this blue one right here, capsular hydrostatic pressure. So that's the force of the fluid inside of the capsule, okay, pushing back that way. So this fluid, because it doesn't immediately flow away, pushes back, okay? So not as much is coming out because I have these 15 millimeters of mercury pushing back. Then we have the second pressure opposing filtration, and that is glomerular osmotic pressure. So we're gonna abbreviate these things. And so I'll just put how we're going to abbreviate them over here because it's always going to be the same. So HPC, and that's going to be a subscript in the future. Okay, so, and a big P. HPC, and then this one is HP, oh wait, no, I got the wrong letter right here. Okay, let me get rid of that. Okay, sorry. Okay, this is HPG, sorry, hydrostatic pressure of the glomerulus. This one right here is HPC. This one right here is osmotic pressure of the glomerulus. Okay, so we can do a an equation without numbers that we can always use regardless of what our different pressures are. And so it's going to be like this, NFP, whoops, NFP is net filtration pressure. So that's the force that actually gets material out of the glomerulus, is the hydrostatic pressure of the glomerulus minus the sum of the hydrostatic pressure of the capsule plus the osmotic pressure of the glomerulus. Okay, so this force right here, the HP G, is an out force. HPC is an in back to the capillaries, and OPG is in back to the capillaries. Okay, so now if we look at the actual numbers that we have here, 60 is what we're pushing out with, but we're pushing back with 15 and 28. And so we only get 17 millimeters of mercury pushing out. And that's good because if it was just straight 60, can you imagine we'd be making urine well, we do make urine every second, but we'd have to go to the bathroom constantly and we would dehydrate ourselves to death if there was nothing opposing this outward flow of filtrate. Okay, so does anybody have any questions to this point? So question number 6 says, what is the normal net filtration pressure? Is 17. So we want to make sure that this number stays at 17 because it's going to affect another number, which we're going to look at right now. And so I'm just going to wait and see if anybody has any questions on that. Okay. All right, let's move on.
An analogy for this process would be a football player, number 60, trying to run for a touchdown. However, his progress to the goal line is slowed by 2 opposing players, number 15 and number 28. The runner eventually reaches the goal, but not as easily as he would without the resistance. Now let's see what happens when a smaller player carries the ball. Click the football to start the process. Here, the two opposing forces, players number 15 and number 28, add together to counteract a smaller, weaker player, number 43, stopping his forward progress. This situation is analogous to glomerular hydrostatic pressure, too low to overcome the countering forces and carry out filtration. This is referred to as kidney shutdown or acute renal failure. Serious consequences will occur unless increased pressure and filtration are resumed. We will now look at how the nephron monitors and regulates the glomerular hydrostatic pressure in order to maintain a relatively constant rate of filtration.
Okay, so let's talk about that. Okay, I don't know how many of you have ever known someone or heard about someone who is in kidney failure and you're like, oh my gosh, they're super sick and everything. Well, guess what? They aren't. I mean, yeah, they're going to be super sick if we don't take care of the problem. But the source of their renal failure is really quite simple. So I want somebody to tell me, Josh Dixon, what would be the easiest way for you to go into renal failure or acute renal shutdown, whatever we want to call it, or somebody. It doesn't have to be Josh. It can be somebody else. So I'm not going on till somebody. Okay, somebody not high blood pressure. Look at this. See, analogous to low blood pressure in the glomerulus. This dude's not big enough. So I don't have enough blood pressure in my blood vessels. So what would be the easiest cause for us to not have enough blood pressure in our blood vessels? Anybody? Okay, think about when we were talking about blood pressure back a while ago and blood pressure regulation. Yeah, go Marcus, good boy. Exactly, dehydration. And that's nice, yep. And that's the problem with being dehydrated, you guys. You could go into acute renal failure. Your kidneys could shut down if you don't drink enough water. Is that scary? Yeah, it is. So make sure you're drinking lots of liquids, especially because drinking lots of liquids cleans out your pharynx and it drives down any coronavirus that you might have into your stomach, and then your stomach acid will break up your coronavirus. So drink all the time. But yeah, it's just as simple as being dehydrated that would cause us to go into renal failure. Okay, so now what? Okay, so here is this idea right now. It says, we will look now at how the nephron monitors and regulates glomerular hydrostatic pressure, because that's what we want to do. We want to make sure that our hydrostatic pressure isn't too high, because then we filter too much and we don't have the opportunity to reabsorb material, or we don't filter enough and then toxins and stuff can build up in our body, and then that doesn't get filtered. And so we have to have, obviously, homeostasis, because what is our theme this semester? Maintain homeostasis. We need to make sure that our nephron is making sure that we have this next thing we're going to look at, glomerular filtration rate, that has to stay at a normal level. Okay, whoops, hang on. Let me answer this. So Josh, so dehydration equals lower blood volume, causing lower blood pressure, causing kidney failure, not because NFP is negative, just that NFP is too low. And actually, it doesn't have to be 0. If we drop 15% below that 17, so if we were to drop to about, what's 15%? So that'd be 1.7 plus 9, 2.6. So if we were to drop to about 14.5 millimeters of mercury, kidneys would shut down. Okay, so it doesn't even have to be 0. Just a 15% drop in hydrostatic pressure will make it so your kidneys don't filter like they should. So even yeah, it is, yikes. It is really scary. So that's why we've got to stay hydrated. But fortunately, a lot of food that we eat, especially if we're eating plant material, has a lot of water in it. So we can get the water out of that too if we're not drinking water. But you know, if you're soda guzzlers like me, it's still water, you guys. You just got a lot of sugar and stuff in there that your body doesn't need, but water's water no matter what you find it in. So as long as you're drinking and not alcohol, that doesn't work. We'll learn about that in a couple of weeks.
The total amount of filtrate formed by all the renal corpuscles in both kidneys per minute is called the glomerular filtration rate, or GFR. In normal kidneys, the 17 millimeters of mercury of net filtration pressure produces approximately 125 milliliters of filtrate per minute.
Okay, so I'm going to stop that. So question number 7 says, with the glomerular filtration rate of 125 milliliters per minute, how much plasma would be filtered in a day? We'll get to that because she's going to tell us. But I want you to highlight or underline or something, glomerular filtration rate of 125 milliliters per minute. Okay, that's a number you got to remember. Okay, so this is homeostasis, glomerular filtration rate. So what does that mean? All of the glomeruli together in your 2 kidneys every minute produces 125 milliliters of fluid. Now, that's a lot of fluid. So let's listen how much fluid, and then we'll talk more about that.
This translates to about 180 liters in 24 hours, nearly enough to fill a 50-gallon barrel.
Okay, holy crap, you guys. How much is filtered a day? 180 liters in 24 hours. Okay, friends, how much blood do we have? How many liters of blood do we have? Show me somebody, because we're going to participate here. Get your Josh on, get your chat on. Yes, good. Okay, everybody's perfect. But how much of that is actually cellular? Or how much of it is actually water? Of that 5.25, how much is water or plasma? Yes, 55%. So just over what? How many liters? Okay, so yeah, 2. We're going to go ahead and go with 3 because 3 is a good number to look at. Okay, so if I have 3 liters of fluid that I have in my body, I produced 180 liters of filtrate. So what does that mean? Did I urinate out all of my, how do I have 180 liters to filter? What's going on in my kidneys? What am I going to do with this 125 milliliters every minute? Am I going to pee that out? Yes. Yay, Josh Dixon. Exactly. So reabsorption. That is what we're going to do. And Josh Quinlan. Okay. So I forgot I got 2 Joshes right now. So yeah, I'm going to reabsorb. And guess what? How much do I reabsorb? 99%. So out of this 125 milliliters per minute, I only excrete a milliliter. Okay. So 99% of everything that I reabsorb. So also, what does that mean? If I go with my total blood volume of 5.25 liters of blood and 180 liters is filtered a day, that means I filter my blood 36 times a day. Wow. Okay, so as it's going through my kidneys, it gets my entire blood supply in one day is filtered 36 times. And why does it have to be filtered 36 times? Remember that I said the material in here is isotonic. So 1 round just takes out the same amount of, it's like half-lives, okay? Whatever urea is in my bloodstream, that amount of urea goes out into my capsule, but I want to get rid of all of it. So, and the bad thing is that I reabsorb urea as well. So I got to keep filtering and filtering and filtering and filtering during the day to finally get rid of all the bad stuff. Okay, so how do we regulate this? How do we keep this 125 mil? Oh, you know what, you guys, let's do this. Let me go to my whiteboard because I have a little equation that I want you to do. Screen share my whiteboard. All right, share. Okay. Which are you guys seeing? Are you still seeing? Are you seeing my whiteboard? Let me say yes. Okay, sweet. All right, so let's see if I can do this the way I want to. Yeah, I think I should be able to. So I'm going to stretch this way out. Okay, so what number do, oh, it's not going to let me write backwards. Oh, I know. Okay, so let's do this. All right, so what number do we want to keep in homeostasis? Okay, yes, my 125, yeah. Well, what actually before my NFP, I want to keep my GFR. So I'm going to put that's my GFR. Oops, GFR. Okay, so that's the one that I ultimately need to keep normal. Okay, so then what makes my GFR be 125 milliliters per minute? My NFP of 17 millimeters of mercury. Oops. Okay, so let me draw. Okay, so an NFP of 17 millimeters of mercury gives me a GFR of 125 milliliters per minute. Okay, now let's put this. Okay, what gives me an NFP of 17 millimeters of mercury? Is
HPG minus the H, or the
right.
HPG plus OPG, that thing.
Good, but I'm just going to put HPG for now, and what HPG number will give me an NFP of 17?
60.
Yes. Yay. Okay. All right. Now, let me put that in there already. Okay, what is going to give me an HPG of 60? Oops. What leads into my glomerulus? If the blood pressure inside of my afferent arterial is 60, then that's going to give me an HPG of 60, which will give me an NFP of 17, which will give me a GFR of 125. Now, here comes the fun one. This one, you're going to go, oh, okay, I finally get everything, well, I hope at this point. So what gives me an afferent arterial blood pressure of 60 millimeters of mercury? Any guesses?
Blood pressure?
Yay! Exactly. Of what?
120/80.
Yeah. So now do you guys see why do I have to keep my blood pressure at 120/80? So that way down here at the bottom, I will have a GFR of 125 milliliters per minute. Isn't that so beautiful? Say yes, it is, Miss G.
Yes, it is, Miss G.
Thanks, Nicole. All right, so now what we want to look at is how do I regulate this 120? Oh, yes, let me find. Because remember, Josh, as you go down and you spread out, you're going to have less blood in your blood vessels. So in your afferent arterial, and we are freaking, how many times have we branched. So we came down the abdominal aorta, we branched to the renal arteries, we branched to the interlobal arteries, we branched to the arcuate arteries, we've branched to the interlobular arteries, we've branched into thousands and thousands and thousands of our afferent arterioles. So now I just have a little trickle of blood getting into my afferent arteriole, but that's higher than all the rest of my capillary beds because it's short. It's coming directly from that interlobular artery and right to my glomerulus. But if I'm out in my tissue beds, I branch and branch and branch and branch and branch, and finally my arterioles are going to my capillary beds. So you got to remember, you got not a lot of flow. Remember, capillaries are only as wide as a blood vessel is. As a blood cell is. And so there's just a trickle of blood going through there. Is that going to have very much blood pressure? Absolutely not. Okay, and it only has about 35 millimeters of mercury. But because we've got this short, stubby arteriole that's wide, there's a whole lot of blood compared to regular arterioles coming into the arterioles, the afferent arterioles within the kidneys. Does that help? I know you said gotcha, but is that good? Perfect. Okay, so now we're going to look at regulation. We're going to look at two regulations today. Let's see. So I'm trying to figure out how far to take you on this, and yeah, we're good. Okay. So there's two places we can regulate. I can regulate, well, actually, let's go over here. So if my GFR was, let's say, 85 milliliters per minute. So it's not very high. What would I do to make it higher? If this were only 85 right here. What numbers would need to change?
My blood pressure.
Yes, your blood pressure. Now, is your blood pressure, so exactly, increased blood pressure. So if I were to increase this pressure right here, would it affect just the kidney?
It would affect everything trickling down.
It would affect everything in your whole body. And who's going to complain about it?
The brain?
The brain, right? Your brain's going to go, holy crap. Because remember, you've got those baroreceptors in the aortic sinus and the carotid sinus. And if those baroreceptors detected a big enough increase in this to get this back to normal, what would they do? They'd shut it down. So it's only in times where we really have to go out here, we'll learn about that later when we get actually into the kidney, we don't want to change systemic blood pressure if we can avoid it. We're going to change it if it's really having a drastic effect in the whole body. If your brain goes, man, this is just too low and I can't handle this. Can you please do something to raise it? Otherwise, we're going to stop right here. And we're going to affect just this portion. And we're going to leave systemic blood pressure alone. And we're just going to work right here at the afferent arteriole and down this way, as I scribble all over it, to make things better. Okay, so does that make sense to everybody? Hopefully. Okay, good. So here we go. We are going to just work from here and nowhere else. And that's called autoregulation. So, oh, let's put one more little, well, actually, two more things. So I'm going to put some little ideas to remember. Okay, so the first thing, so this is going to go with question number 7. With a glomerular filtration rate of 125, you get 180 liters a day. So too high GFR. So what do we care if we have our GFR is too high? Okay, we get too much water and solute will be lost. Okay, so we don't want that, right? That's a bad thing. And then what if we have a too low of a GFR? Whoops, that means too little. Whoops. Water and solute will be filtered. And so material will stay around, and I won't be cleaning things out and regulating like I should. So, so yeah, it's homeostasis thing. We got to stay right at 125 because too high is bad, too low is too bad, or is bad. All right, so let's go on and see what your body's going to do about that.
Fortunately, 99% of this volume will be reabsorbed as the filtrate passes through the tubules. The glomerular filtration rate is directly proportional to the net filtration pressure, so a fluctuation in any of three pressures previously discussed will change the GFR. Prolonged changes in normal GFR will cause either too much or too little water and solutes to be removed from the blood. Let's look next at how the body attempts to counteract the normal daily fluctuations of systemic blood pressure by initiating an autoregulation mechanism that maintains normal GFR.
Okay, autoregulation means it's going to happen within the kidney itself. So like I said, we're going to start at the afferent arterial level, and that's what we're going to affect in each nephron. So remember, each nephron has an afferent arterial. So we are autoregulating nephron by nephron, which I think is so cool. I mean, what? We have 1 million nephrons. So we are fixing every single nephron as long as they're functioning properly. Okay.
During normal conditions, systemic blood pressure registers approximately 120 millimeters of mercury. The diameter of the afferent arteriole is normal, as is the glomerular hydrostatic pressure. These conditions provide a normal glomerular filtration rate of 125 milliliters per minute. When blood pressure fluctuates during normal daily activities, autoregulatory mechanisms of the kidney alter the diameter of the afferent arteriole in order to maintain a relatively constant glomerular filtration rate. Now click the exercising button to increase the cartoon character's activity level. During mild exercise, the systemic blood pressure increases to 140 millimeters of mercury. If the afferent arteriole remains at the normal diameter, the 17% increase in glomerular hydrostatic pressure will cause a similar increase in GFR. If allowed to continue, this increase will quickly cause severe dehydration. To avoid extensive fluid loss, click the afferent arteriole to initiate autoregulation. The autoregulation mechanism decreases the diameter of the afferent arteriole, decreasing the glomerular blood flow. The glomerular hydrostatic pressure and GFR return to normal, even though the mild exercise continues and the systemic blood pressure remains elevated. Now click the normal button to reduce her activity level back to normal.
Okay, so if we look at question number 8, in an exercising individual, the afferent arteriole will constrict to avoid excess fluid loss. Okay, so I know you're going to go, why did we constrict that? Yes, okay. Yeah, HPG is what fluctuates all the time. Because OPG never changes. So the amount of albumin that you have within your blood never ever changes unless you've got some protein malnutrition or liver disease or something like that. And capsular hydrostatic pressure is just based on how much comes out. So that can fluctuate, but really what is the one that's going to change the most is hydrostatic pressure, the glomerulus. So that's what we're affecting. Okay, so now I wanted to stop here. Anyway. All right, so why did we constrict this? I thought every time you constrict something, your blood pressure goes up. That's the blood pressure in that vessel. But that's not what we're concerned about. We're concerned about the pressure inside the capillaries. And remember, there is no smooth muscle in the capillary wall, so I can't do anything to reduce that pressure other than change the amount of blood that goes in. So if I constrict the afferent arteriole, that reduces capillary blood flow, and therefore, because that's what's causing the hydrostatic pressure in the glomerulus in the first place, is the amount of blood that's in there. So by reducing the amount of blood, by constricting the afferent arteriole, that reduces the amount of flow into the glomerulus and reduces the blood pressure. So it's counteracting, because my blood pressure out in my body is still 140. And so, you know, if I'm still exercising, like I worked out, like, oh my gosh, my workout this morning was crazy. And so my blood pressure, I'm sure, was at least 140, but I can't have that down at the kidney level. So like I said, nephron by nephron, I will regulate each and every afferent arteriole. I'll make them constrict. So how do you do that? We're going to get to that in a minute because that's really fun. Okay, so remember, with high blood pressure, high systemic blood pressure, the afferent arterioles will be constricted. Okay, and then we're going to write something down in a minute.
Reducing the activity level returns the systemic blood pressure to 120 millimeters of mercury. The afferent arteriole dilates to maintain normal glomerular hydrostatic pressure and GFR. Now click the relaxed button to further reduce her activity level. During periods of relaxation, the systemic blood pressure may drop to 100 millimeters of mercury or lower. If the diameter of the afferent arteriole remains normal, blood flow into the glomerulus is reduced. This in turn causes a reduction of glomerular hydrostatic pressure and GFR. To avoid poor filtering of the blood, click the afferent arteriole to initiate autoregulation.
No, it's supposed to dilate, and it didn't do that. So let's make a little note up here. Right here, that low, because we already put in an exercising individual, the afferent, so that would be high blood pressure, high systemic blood pressure. So we get vasoconstriction during high systemic blood pressure, but what about low systemic BP causes vasodilation? Okay, so make sure you remember that. So that, and it didn't work with the little thingy, but it then dilates. Okay, so now what we want to take a look at is, how are we getting this smooth muscle to do this? So remember when we were doing blood pressure regulation, that we didn't always have to tell the smooth muscle to vasoconstrict from the vasomotor center. So we didn't have to go from the medulla all the way down to the smooth muscle to affect a change. So we're not going to involve the brain at all. This is going to be localized. It's just going to be right at the afferent arteriole. So how are we going to get it? How are we going to get it to vasoconstrict? Well, that's the fun part. Oh, to get rid of that.
Okay, well, friends, since that froze on me, what's going to happen is that the afferent arteriole will dilate.
I forgot I said that.
Bigger so that more blood can come in, therefore raising the hydrostatic pressure within the glomerulus and increasing GFR back to the normal limit.
There you go.
One of the mechanisms that provides autoregulatory control over renal processes is the result of the inherent tendency of vascular smooth muscle cells to contract when stretched. This allows the diameter of afferent arterioles to respond to changes in blood pressure. Therefore, when blood pressure in an arteriole increases, the walls of the vessel automatically constrict, reducing blood flow through the arteriole. Conversely, low blood pressure reduces this reflexive constriction, so the arteriole dilates and blood flow is increased. In renal autoregulation, this is called a myogenic mechanism. Click the weightlifter to see an animation of this mechanism in action. Stretching the arterial wall causes a reflexive vasoconstriction. As long as pressure continues, the vessel will stay constricted. Click the weightlifter to make him relax. When pressure against the vessel wall is reduced, the vessel dilates. Changes in blood pressure therefore directly affect the constriction or dilation of the arteriole, and so glomerular blood flow.
All right, so this is an inherent characteristic of vascular smooth muscle that if you try to stretch it, so think about you're wringing out a towel, okay? So remember that's how vascular smooth muscle works. So if you open up that towel, all of those little myosin proteins that are wrapping through the skeletal or through the smooth muscle to make it, you know, scrunch up, twist up like a towel, they don't want you to unfold the towel. And so as you, from the inside, so as you try to unfold the towel from the inside, then it just closes up on you even more. So in question number 9, 2 mechanisms that provide autoregulatory control over renal processes include A, this myogenic mechanism. Okay, so myogenic mechanism is, I'm trying to find my thing. Okay, so that is, so the inherent tendency of vascular smooth muscle to constrict when stretched by blood pressure inside the blood vessel. Whoops, blood vessel. Okay, so then what if this pressure is gone? Then it's going to expand back out again. So it'll plump back up. Now it's not going to get super big, but that's how vasodilation is going to happen, is just in the absence of pressure, then the smooth muscle relaxes and the diameter enlarges. Okay, so under high blood pressure, so high BP, oops, causes vasoconstriction, while low BP causes, whoops, vasodilation. Okay, all right, so are we good with that? I'll leave that for just a second. And then we're just about done with this part, and then we'll look at one more thing. I have a meeting at 11, so you know we're going to be, it's not going to get too low, because what's going to happen, so Josh, for those of you that didn't see, it seems like this would turn into a positive feedback loop. What stops it? No, it's not positive feedback, because as soon as this gets down to a less pressure, as he vasoconstricts, once the pressure drops, then it stops constricting, and it stays at that point until it relaxes, and then it dilates. So it'll get to an end point. It just doesn't get tighter and tighter and tighter, because you know at some point you're restricting the blood flow. And so as soon as you restrict the blood flow, then the vascular smooth muscle goes, oh, okay, I'm happy with that. I will no longer constrict. So does that answer your question? Okay, great. All right, anybody have any questions before I go on to the next mechanism? Okay, so here we go.
Click the weightlifter to see this activity again. A second regulatory mechanism is the sensitivity of the macula densa cells of the juxtaglomerular apparatus to the concentration of sodium chloride in the filtrate, which is proportional to the rate of filtrate flow in the terminal portion of the ascending loop of Henle.
Okay, what the crap did all of that mean? Because that's a whole lot of words. You're like, I don't understand. All right, so right here, let me annotate this. Okay, so green. Okay, so right here, this portion is the connection between, so we're going from thick ascending limb, that's how we abbreviate it, thick ascending limb of the loop of Henle to the distal convoluted tubule. Okay, so what the nephron's going to do, it's been proximal convoluted tubule, it loops down, comes back around, comes up, and it goes up right in the V that's formed between the afferent arteriole and the efferent arteriole. So right at this point, as we're transitioning from thick ascending limb to distal convoluted tubule, I have a set of cells right here. So these cells right there, called the macula densa. And the macula densa are chemoreceptors. Oh. Okay, so what are the chemoreceptors chemorecepting? What are they detecting? I'm just going to write it because that's easy. Sodium chloride concentration. Okay, so they're looking for slow sodium chloride concentration in the filtrate. All right, so here's what we've done. And this is the thing that Mr. Burke and I did yesterday, because what's happening in the nephron is very much like what happens on our conveyor belt. And so you want to start out with a rate on your conveyor belt that is proportional to the amount of workers that you have on the conveyor belt. And so the workers on your conveyor belt are all the proteins, the transport proteins that are trying to reabsorb everything you just filtered. And so what we're going to do is we're going to turn on the crank or the conveyor belt at the beginning by control. So the rate of flow, how fast is my conveyor belt going? And so that's going to be how much flow is coming into the glomerulus, and we determined that right here. So this turns on the conveyor belt. I'm so anal, you guys. Okay. All right, so the pressure in the afferent arteriole starts the whole process. And so then it's going to crank along, and we're going to take a look at what our workers on either side of the conveyor belt can do. Can they take out everything that we want? Well, now when you get to the end of a conveyor belt, you have to look at your product. You can't just say, okay, yeah, everything's good. Because what if you're putting a car together and somebody missed a bolt along the way? Well, then your tire's going to fall off. Okay, so we can't have that. Everybody has to do their job properly, and you have to be checked at the end. Remember on those Fruit of the Loom commercials, for most of you, you weren't even born yet, but those Fruit of the Loom commercials where they had Inspector 19 would say, oh yeah, those the stretchiness, the elastic in your underwear and everything is perfect. And so then you could sell that product. And there was also that little thing, inspected by Inspector 19. So that's what the macula densa is. Okay, so they regulate the conveyor belt. Okay, so does that make sense? We're checking to see how much sodium chloride do we have here at the end. If that's the right amount, I don't have to change the speed of my conveyor belt. But if it's too much sodium chloride, then it went by too fast. And if there's too little sodium chloride, it went by too slowly. I didn't filter like I should. Okay, so we start with the afferent arteriole. We stop, or we adjust with the macula densa. And so we decided based on, well, what was the pressure coming in? Okay, so the afferent arteriole already figured that out, and then we checked, we made sure, we inspected the product, and then we made any adjustments, any fine-tuning adjustments that we need to do. So 9B is the tubuloglomerular mechanism. And so that's going to involve the macula densa. Okay, so these chemoreceptor cells that are right here, between the afferent and efferent arterial will measure the filtrate concentration and then change accordingly. And so let's look at what they're going to do to change accordingly.
Click the high flow button to see this auto-regulation mechanism at work.
So this is number 10.
A higher than normal flow of filtrate resulting from an increased GFR causes the concentration of sodium and chloride ions in the filtrate at the end of the ascending limb of the loop of Henle to increase. This high sodium chloride concentration stimulates the macula densa cells to release vasoconstrictor chemicals, which cause the afferent arteriole to constrict. The result is a lower GFR, lower filtrate flow, and increased tubular reabsorption of sodium and chloride ions.
Okay, so question number 10, high osmolarity or high sodium and chloride in the ascending loop of Henle. You can put a little note, macula densa, because that's what actually determined, that detects it, will cause afferent arterioles to constrict by releasing a vasoconstrictor chemical. Okay. Now, what about if it's too low? Let's see what happens.
Now click the low flow button to see its effect on regulation of the GFR. A low rate of filtrate flow, and therefore low sodium chloride, in the terminal portion of the ascending loop of Henle is also sensed by the macula densa cells. This condition is usually the result of low GFR caused by low blood pressure.
Okay.
In response, these cells initiate two effects. One, they decrease secretion of the vasoconstrictor chemicals. This leads to dilation of the arteriole and so increases blood flow, glomerular hydrostatic pressure, and the GFR. And two, the macula densa cells signal the granular cells of the afferent and efferent arterioles to release renin into the bloodstream.
Okay, so make sure you write down this by that question, because it asks you what the high is, but we also want to know what the low is. Okay, so when there's not enough sodium chloride in the filtrate, then the macula densa cells will release less vasoconstrictor and then signal granular cells. So granular is the same as the JG cells, because it has JG in the, oh, I didn't put that. JG cells mean juxtaglomerular. Oh, here's where they are. Okay, so JG cells, juxtaglomerular cells. Okay. All right, so we've got what happens with high. We're going to make the vasoconstrictor chemical. We're going to vasoconstrict the afferent arteriole. The JG cells then we'll make, under low flow, then we'll make less vasoconstrictor chemical, but then the JG cells, and this is really important, we'll talk about renin later, not today, don't worry, will release renin. Okay. All right, now the last part of this page is right now on sympathetic stimulation.
Now click the granular cells of the afferent arteriole to see the effect of renin on the regulation of the GFR. In the bloodstream, renin triggers a series of events that increase the level of the hormone angiotensin II. You can see this process in greater detail in the blood pressure regulation topic of the cardiovascular system module. In the kidney, increased angiotensin II causes constriction of the efferent arteriole. This causes the blood flow out of the glomerulus to slow, thus increasing the glomerular hydrostatic pressure and restoring the glomerular filtration rate to normal. Angiotensin II also stimulates the release of the hormone aldosterone. The effects of aldosterone in the kidney will be discussed in the late filtrate processing topic of this module. Sympathetic nerve fibers innervate all blood vessels of the kidney as an extrinsic regulation mechanism. During normal daily activity, they have minimal influence.
And then it froze on me right there. So I'm going to type in, what if you have blood loss? like what's going to happen with this poor guy. So what is sympathetic stimulation going to do with blood loss? Okay, extreme low blood pressure. So two things, we're going to get constriction of, renal arteries. Okay, so we're even going to restrict right coming in. So, so these renal arteries here, this one right here, so these, all of the renal arteries. Okay, so afferent arterioles and all of the arteries coming in is going to decrease, and then B is shunt blood to other areas to reduce the effects of blood loss. Okay, so more important areas are going to get the blood flow and the kidneys are not. Okay, so even when you're exercising, when you're in sympathetic stimulation, you don't make much urine because that's a waste of fluid because you're already going to be sweating and you need your blood volume. Remember when we were looking at the basketball playing guy, we need the blood volume in our muscles. And so we're going to shunt the blood away from our kidneys. We do not want to lose water through our kidneys. And then one more thing, so this is just on a side note, you can put this at the bottom. If GFR is low, and this is a thing we wanted to always remember because we are more often in a low blood pressure situation than we are in a high blood pressure situation. So we have to fix that. So if GFR is low, afferent arterioles dilate while efferent arterioles, oh my gosh, I can't spell that, constrict. And so why would constriction of the efferent arterioles be good? Well, because now we're keeping blood longer. So on the front end, we're delivering more blood into the glomerulus, and on the back end, we're letting less blood out. Okay, so blood will hang around within the glomerulus longer, therefore creating more osmotic pressure. I mean, more hydrostatic pressure, sorry. Okay, so that's all for this page. I know that's an enormous amount of information, but that's all for that. So we're going to go to the next page on early filtrate processing and then finish those questions, and then we'll be done. We can do late filtrate processing really easily. We're not going to watch anything for that. But I will put this video in as well, just all this by itself without me talking over the top of it, so that you can watch this as many times as you want as well. Okay.
Miss G, I missed number 9. What was number 9?
Number 9 is myogenic mechanism, is A. So that's when the smooth muscle constricts of the afferent arteriole. And then B was tubuloglomerular mechanism, and that's what we just described with macula densa.
Thank you.
Yep. Okay, so let's, how do I want to do, oh, okay. All right, so that's all for that we're gonna watch. Oops, let me get rid of my drawing. Okay, so now the next thing that we're gonna do is watch the second one, and it's not as long. Let me find it. This one.
Once the filtrate is formed, the early...
Okay, so can you guys see the early filtrate processing video thing? Because I don't know if I'm still sharing my screen properly.
Yes, you are.
Okay, perfect. Thank you. All right, here we go.
Tubular segments of the nephron reabsorb solutes and water back into the blood to restore its volume and composition. They also remove some solutes from the blood and secrete them into the filtrate to fine-tune the blood's composition. Your goals? The relationship of glomerular filtration and tubular reabsorption is something like a parent who cleans a child's room by arbitrarily throwing much of the room's contents into the trash box. That's analogous to glomerular filtration. But as soon as the parent is gone, the child quickly reclaims his favorite things from the box. This rescue of valued substances is like the process of tubular reabsorption of solutes back into the blood. All objects remaining in the trash box will be discarded as waste. To be reabsorbed into the blood, substances in the filtrate must cross the barrier formed by the tubular cells. There are two reabsorption pathways, the transcellular and the paracellular. Most solutes that are reabsorbed use the transcellular pathway. They diffuse or are actively transported through the luminal and basolateral membranes of the tubular cells into the interstitial space and then into the paratubular capillaries. Click the arrow to see an animation of the transcellular pathway. The second pathway is the paracellular one through the tight junctions into the lateral intercellular space. Certain tight junctions are not as tight as the name implies and will allow this pathway while others will not. Click the arrow and follow it through the paracellular pathway. Although most substances use the transcellular pathway, water and certain ions use both paths, especially in the proximal convoluted tubule. Both pathways lead into the interstitial space, then through the endothelium of the paratubular capillaries into the blood. Click either arrow to see its pathway again. To summarize, the transport of sodium ions has two important direct results. The last question is,
Sorry, I
the next question.
messed up. I decided we needed to see all of this stuff.
The previous topic, glomerular filtration, demonstrated that the force driving the formation of the filtrate is blood pressure within the glomerulus. We now turn to the question of what drives reabsorption, which reclaims the valued substances. Let's begin with the reabsorption of water by diffusion. For each of the following questions, select the correct answer by clicking the appropriate box. How can we cause water to diffuse from the lumen through the tight junctions of these generic tubular cells into the interstitial space? Yes, water will move from its higher concentration in the tubule through the tight junctions to its lower concentration in the interstitium. Water will also move through the plasma membranes of the cells that are permeable to water.
Okay, so here's what we have to do in this situation. If we want to absorb water, we need to make the outside here, so the interstitium outside of the tubule cells, we need to make this more concentrated. Okay, so higher osmolarity, so that the water, because remember, water is going to go from dilute to concentrated. So we need to make it more concentrated than this over here so that water will want to go this way. Okay, so that's what we're looking at. Increasing the osmolarity of the interstitium means make this interstitial fluid out here more concentrated.
The next question then is, how can we increase the osmolarity of the interstitium? Yes, transporting sodium into the interstitium will raise its osmolarity. Water will then diffuse from the tubule through the tight junctions and permeable plasma membranes to the interstitium, equilibrating the two osmolarities.
Okay, so what we need to do then is actively transport, because I want to make this really salty out here. So I need to increase it. Eventually I'm going to get past equilibrium, but I want to keep pumping sodium out here to the interstitial fluid. So what needs to be on this basolateral membrane? So this is called the basolateral membrane. This is the luminal membrane because it's on the side of the lumen, and this is basolateral. So tell me, friends, what do I need so that I can pump sodium into the interstitial fluid? That wasn't rhetorical. Yay, I do want a sodium potassium pump, but that's exactly right. Okay.
I said it, but I was still on mute. I'm talking to myself over here.
Primary sodium ion concentration
Nice.
resulting from the basolateral transport affect the activity at the luminal membrane.
So now, hang on, let's go to this question. So now it's asking if I'm pumping stuff out on this side, what's that going to do on this side? It says, how will a reduction in the intracellular, so the amount of sodium that I have inside of the cell, because I pumped it out on this side, what will that do on this side?
Yes, the transport of sodium ions through the basolateral membrane will cause more ions to be reabsorbed through the luminal membrane.
Okay, so what two things did I just reabsorb in that picture? Somebody? Yay, exactly. So I pumped the sodium out. So Josh said sodium and water. So I pumped the sodium out and then the water got reabsorbed. And then because I had less sodium in here, then the sodium went too. So can I use this sodium transport for something else? Yes, I can. Let's take a look.
To summarize, the transport of sodium ions has two important direct results. One, the interstitial osmolarity increases, causing water to diffuse out of the tubular lumen. And two, the lowered intracellular concentration causes additional sodium ions to be reabsorbed through the luminal membrane.
Okay, so for question number 4, it says summarize, we're on the back of the first page. Summarize reabsorption in the proximal tubule. Okay, so first, and I'll just go through a quick answer with you, type a quick answer in so that, oh, except I don't know where my little, it's not letting me annotate now. Oh, well, okay, so I'll just tell you. So first, I increased the osmolarity by pumping sodium into the interstitium. And then I reabsorbed water, and then I reabsorbed sodium. And we'll see if we get through this. Yeah, I will find it. The other material that gets reabsorbed. Okay, so first, sodium is pumped into the interstitial fluid. Water is reabsorbed because of that increased plasma osmolarity. And that, or not plasma, but interstitial osmolarity. And then sodium will be reabsorbed from the lumen. Okay, I'm gonna have to go in a minute, but let me show you, and then I'll probably just make another little video to finish this stuff off that you don't have to be here for after my meeting.
This provides more sodium ions to be actively transported and enables the cycle to repeat. In addition, as we will see in the following pages, sodium ion transport enables the reabsorption of most substances in the nephron. We will now begin a tour through the renal tubules. We'll see how the specialized cells in each region accomplish a different stage of filtrate processing. Our first stop is the proximal convoluted tubule, where major reabsorption of valued substances occurs. We'll look first at the activities occurring at the basolateral membrane of the tubular cells. Click the box on the basolateral membrane to start the tour.
So here's where we actually see the pumps working.
The reabsorption of many substances from the glomerular filtrate in the PCT depends directly or indirectly on the active reabsorption of the sodium ion. The cellular structure responsible for this process is the sodium-potassium ATPase ion pump located in the basolateral membrane. Orient yourself to the parts of the scene and then click the sodium-potassium pump to activate it.
Okay, so here we are inside of the cell. This is outside of the cell.
Carries out primary active transport of sodium ions out of the cell and potassium ions into the cell.
And this is a cell that
As it
lines the
yields its
tubule.
energy, ATP is converted to ADP and an inorganic phosphate ion, or PI. The sodium-potassium pump is found in the basolateral membrane of many regions of the nephron. Now click the ion pump again to see its effect. Watch what happens to the fluid in the interstitial space as a result of the ion pump's activity. Notice that the interstitial fluid is becoming more concentrated, as indicated by the darker color. The net effect of the ion pump's activity is to decrease the sodium ion concentration inside the cell and increase its concentration outside the cell, thereby increasing the interstitial osmolarity. However, this increased osmolarity around the PCT soon draws water from the tubule, decreasing the interstitial osmolarity again. And together, the water and solutes diffuse passively into the peritubular capillaries and are carried away. If you didn't notice the interstitium darkening, repeat the activity by clicking the ion pump. Otherwise, click the basolateral membrane to see additional features. Now notice two additional transmembrane proteins in the basolateral membrane, a potassium ion channel and a glucose carrier molecule. Click either protein to see its activity. The glucose carrier molecule binds only to glucose and transports it across the basolateral membrane by a passive mechanism called facilitated diffusion. Glucose can move either into or out of the cell depending on its concentration. Since in the situation shown here, its concentration is highest in the cell, glucose moves out of the cell into the interstitium. Now click the potassium ion channel. The potassium ion channel lets most of the potassium ions diffuse from the tubular cells back into the interstitium. It prevents the sodium-potassium ATPase ion pump from causing potassium ion depletion in the blood or excess accumulation in the cells.
So I think this is really cool here because really what do we only want? We only want sodium out here. But if I kept messing with my, my sodium potassium pump, pushing the potassium in, eventually there wouldn't be any out here and my pump would stop. And so we have these open channels so that the potassium it comes back in, it goes back out, it comes back in, it goes back out, so that we just deal with the movement of the sodium. Okay, we're going to finish we're going to look at the front end of this, and then we'll stop for now.
In addition to the molecules you see here, many other substances also cross the basolateral membrane by similar mechanisms. The luminal membrane of the proximal convoluted tubule contains many transport proteins. Here you see 3 sodium-hydrogen countertransport carrier molecules and 2 sodium-glucose cotransport carrier molecules. The activity of all these carrier molecules depends on sodium-potassium ATPase ion pump activity in the basolateral membrane. Click any of the transporters to see their activity. When you have seen each, click the luminal membrane to see the activity of the entire membrane. The cotransport or symport carrier molecules carry both sodium and glucose into the cell. The reabsorption of glucose depends on the movement of a sodium ion down its concentration gradient from high extracellular to low intracellular concentrations. This is an example of secondary active transport. Glucose now moves down its concentration gradient to the basolateral membrane, where it is transported into the interstitium by facilitated diffusion, as seen previously.
Okay, so what's going on here, this is called secondary active transport. So what I'm trying to do is build up glucose on the inside. So eventually I'm going to have more glucose on the inside of the cell than I'm going to have out here, but I want to take every last glucose molecule. So in order to fuel that active transport, what we do is put the sodium in here to open the gate. So the the glucose is going to fall in, the sodium will come in, and that sodium will open up the channel. Now, why does the sodium want to come in? Because over here on the back end, oh, now it wants to work for me. Because out here on the back end, I'm pumping sodium out, so that draws the sodium in this way. So then the sodium wants to fall in here. So because of the primary active transport of sodium out here, I get the secondary active transport of glucose on the front end. So this is all my absorption of my glucose. And then remember, now that I have lots and lots of glucose molecules on the inside of my cell, then that little transporter that we saw in the last slide is now just going to act by diffusion, where the glucose is going to leave the interior of the cell, go out into the interstitial. Okay, so the front end, let me draw a little picture. So here is the luminal membrane of a cell. Here's the basolateral. So this is the back end. This is the front end. So remember, we're doing active transport of sodium on the back side. And then the paratubular capillary would be out here. So this is a capillary out here. So we pumped the sodium to the outside, in came water, in came sodium. So water came in, sodium came in, and then went into the tubule. So now on the back, on this side, I have a regular glucose molecule. And on this side, that's this right here. I have this co-transporter on the front side. And so now the sodium wants to go in because I'm pumping it out on the back side, and then the glucose will go with it. And so I'm building up lots of glucose inside of my cell, which will then just diffuse out of the cell. So I hope that helped. Okay, we just got one last thing to do, and then we'll be done for now. Okay, good.
Now click a sodium hydrogen transport. The countertransport or antiport carrier molecule carries a sodium ion into the cell and in exchange secretes a hydrogen ion into the filtrate. Here in the PCT, this activity is dependent on the movement of a sodium ion down its concentration gradient from high extracellular to low intracellular concentrations. This is an example of secondary active transport driven by the primary active transport of the basolateral membrane. The hydrogen ion being secreted here is generated in the cell for acid-base balancing purposes. Now, click the sodium glucose transporter to see its glucose is vital to the body's normal functioning.
Okay, I'm going to stop this right here because I have to go and our brains are full for right now. I'm not quite done with what I want to show you, so I'm going to come back at noon when I'm done with my meeting and make a last little video. If you want to come into my Zoom meeting then, because I'm just going to Zoom it and record it, you're welcome to. So at noon, I'll be back to finish this off, or you can just watch it because I'll just post it and whatever. So, so there's that. Does anybody have any last kind of stuff that they want to ask me about? And then two, always remember, if you're stuck and you don't know, you know, because this is a really hard way for us to do this, just tell me, Mrs. G, I want to Zoom with you. So, well, let me stop sharing so I can see your cute faces. So anytime that you just want to Zoom with me for a few minutes, I can even do it from my house, and I can, you know, tutor you and help you, and but at least you have this to watch sections of that you don't understand. So if I don't have any questions right at this moment.
What exactly are we supposed to be studying for the chapter 10 quiz?
Oh, so just a minute, Addie, there's nothing in the purple packet. Because if you look at the purple packet, it says exercise, so urinary system physiology, see handout. That's this. So there is nothing in the purple packet anymore until we do reproductive system. Okay. So, and to answer your question, Nicole, in summary, what's going to be on this next quiz is all the way down to the end of question 6 on this page, on the back side. So all the front of the first page and the back of the first page. But I will finish up the back of the first page much more quickly and much easily at 11 or noon. The last one that I make.
So down through the early filtrate processing, all that part?
all through down the late filtrate processing.
Oh, this whole second page. So the
The whole
first two
second page.
pages.
Yep, the
Okay.
whole first 2 pages. Yep. And no, the quizzes are on Canvas, so no quizzes in Zoom. Yep.
Thank you.
Everything's in Canvas. Okay, does anybody else have any last questions? And yes, Josh, everything that you've done in pharmacology on diuretics, we're doing right now. So the physiology should be helping you understand how those diuretics work. Okay, well, then I'm going to stop our recording, and I will be back at noon and record some more, and whatever. Life is just nuts right now. Okay, good luck, and I'll see you tomorrow morning at 9 o'clock for more digestion.